Welcome back, everyone. This is Professor Herring. In this video, we're going to continue our discussion on valence bond theory, specifically looking at how multiple bonds are formed. We're going to talk about restricted rotation around multiple bonds. We're going to talk about counting up numbers of sigma and pi bonds, and then also discuss delocalized pi bonding, or in other words, resonance. Let's begin. So when we talked last time, we looked at how you have different types of hybridization, sp3, sp2, and sp orbitals, depending on the number of electron domains that are needed to be formed. We're now going to talk about what happens to those unhybridized p orbitals that are left over in the sp2 and sp hybridizations. If we look at a molecule with a double bond, like ethylene, we see that each carbon atom has 3 sp2 hybrid orbitals and a leftover atomic p orbital. That would look like the following. We see that one of the sp2 hybrid orbitals overlaps with the s orbital to give the carbon-hydrogen sigma bonds, and 2 sp2 hybrid orbitals overlap, one from each of the carbons, to form the sigma bond between them. Remember, we discussed how sigma bonds result in the head-on overlap of these hybrid orbitals. However, the unhybridized p orbitals will also overlap to form a pi bond, and this is the second bond within a double bond. It's very common for students to mistakenly think that a pi bond is a double bond, but is rather just the second of the double bonds. Because the orbitals used to make the pi bond are above and below the elements involved, it means then that they are restricted from rotating. They would have to rotate with each other. If we were to just take and hold one carbon steady and rotate the other around, and it turns those orbitals away from each other, as illustrated in this image on the right, then that's going to break the bond. Therefore, this process requires energy. Now, it's not impossible, but it does require energy. And our bodies take advantage of this necessary energy that's required, and that's how we can see. There is a molecule in our eyes that is light sensitive. And because of all of the double bonds that are within the molecule, it requires energy to rotate. And when light hits that molecule, when we see something, in other words, it shifts the orientation or the conformation of that molecule. Our brain then translates that shift in the molecule's position into interpreting the light that has come through. And so if you ever stare at a very bright light, and you get those spots in your eyes, those bright spots that don't go away for a long period of time, what's happening is that it's getting stuck in this position on the right, and it's not flipping back into its original position. So we see that bond rotation is actually an important aspect of human life. Now, when we talk about triple bonds, these are similar to double bonds in that in order to form them, we have to have unhybridized p orbitals, but we need to have 2 pi bonds. And so this only occurs when we have sp type hybridization. Again, we need 2 electron domains, and so we have to have 2 hybrid orbitals that are identical. And then we're left over with these unhybridized p orbitals that overlap with each other. And when they overlap, they form the pi bonds. So one thing to notice about this is that in order for those pi bonds to form, there needs to be sufficient overlap. And we talked about trends of the periodic table, how the elements get larger as we go down and smaller as we go to the right. We might expect that silicon, so if we have carbon here, silicon is right beneath it, we might expect silicon to form double bonds. It has a valence of 4 as well, but it turns out that it does not. And the reason for that is because silicon is larger than carbon. If we take 2 carbon atoms versus 2 silicon atoms, there's a large enough difference in size, which means then that the unhybridized p orbitals are too far away from each other within the silicon atom to form double bonds. This is also why we talked about a while back about how carbon has so many different types of molecules it can form. This is essentially why we could never have a silicon-based universe, because silicon cannot form the complicated structures that carbon-based molecules can. All right, now that we've had an opportunity to look at sigma bonds and pi bonds, let's practice. Try and determine how many sigma and pi bonds are in the molecule below. Pause the video and try this on your own, and then we'll work through it together. Welcome back. So one thing you want to remember is that in these types of skeletal structures that some things are hidden. Lone pairs are hidden, as well as hydrogen atoms that are attached to carbons. And the way that you determine the number of lone pairs and the number of hydrogen atoms is by following the rules of valence, which states the number of bonds that an element's going to typically form, and therefore you have to use deduction to figure out what's left over, what's not being shown. So if we draw out this molecule, we can see that we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds and a single pi bond. So hopefully you got that. Now, it's very common to mistakenly call a double bond, or to call any pi bond a double bond. So if you had looked at this and said that there were 8 sigma bonds, then you're forgetting that in order to have the pi bond, we have the hybridized orbitals that are overlapping, and then the unhybridized orbitals that are overlapping. The pi bond is the bond that's down the axis of the nuclei, and the sigma bond is down the axis, and the pi bond is above and below the axis. Let's talk now about delocalized pi bonding. We've looked already at resonance structures and how resonance structures are different representations of reality. In other words, if you look at nitrate, the true structure is an average of all of the resonance structures. The electrons are not actually oscillating, moving around, jumping, and this double bond is not jumping back and forth between them, but rather it's spread throughout the entire molecule. So when we look at the electron domain geometry of nitrogen, we see that it's trigonal planar. It has 3 electron domains. However, when you look at the hybrid orbitals, when you look at the hybrid orbitals, therefore that means it's going to be sp2 hybridized. And if it's sp2 hybridized, then that means it has a leftover p orbital. And then what about the oxygen atoms? In order for them to participate in this delocalized pi system, they must also have leftover p orbitals. And so it turns out that anytime you have hybridization, for whichever elements are quote-unquote participating in that hybridization, what you really have is unhybridized p orbitals that are overlapping to form delocalized pi bonding. And so this whole molecule, since all of the elements involved can be shown as participating in resonance, all of them have an unhybridized p orbital, which means that the hybridization of each of the oxygens is actually sp2. Even though this looks like sp3, we know that it cannot be sp3 because we have to have an unhybridized p orbital in order for it to participate in a delocalized pi system. And because these electrons are spread across the entire molecule, again, that brings added stability. This delocalized pi bonding explains the stability of what are called aromatic hydrocarbons. And we're going to explore these more in chapter 10, but it's important to recognize the difference between localized pi bonds. In other words, the electrons are here to stay, they're not moving anywhere, versus delocalized, where the electrons are spread throughout the molecule. This means that they are less reactive. And so it turns out that the molecule on the bottom is not going to produce a chemical reaction with the same molecule that with the same bromine molecule that the hydrocarbon on the top was reacting with. A way to represent this with benzene is these two resonance forms, which in reality is an average of them. And what we see when we look at the map of when we look at those hybrid orbitals combining, is that we are forming this unhybridized pi system, or this delocalized pi system, that's spread over the entire molecule. So, we've talked already about how do you find resonance. We've talked about resonance as being, or the pattern looking for a lone pair adjacent to a double or a triple bond, where those electrons could be thought of moving between them, as in this molecule represented there. Now again, we know that the reality is the weighted average of these resonance structures. And so it's somewhere in between these two different forms. However, we saw that we can also have resonance when we have alternating double or triple bonds separated by a single bond. That would be shown using resonance forms in the following process. And here's some examples that you might see where we have, again, double bonds, alternating double single bonds. So let's summarize what we've learned about covalent bonding. We know that orbitals overlap to form covalent bonds, and that depending on what type of orbital overlap they are, we either have a sigma bond or a pi bond. Every single bond consists of a sigma bond. Every double bond consists of a sigma and a pi bond, and every triple bond consists of one sigma and two pi bonds. We know that the electron domain geometry determines the hybridization, and that for a tetrahedral, we're going to have 4 identical hybrid orbitals. Trigonal planar has 3 hybrid orbitals, linear has 2, and then we have leftover p orbitals that are what participate to form the pi bonds. So the process for solving these types of problems would be to draw out the Lewis structure, use VSEPR to determine what its shape is. Then, after you determine the electron domain geometries, you can determine what hybrid orbitals are involved in the bonding. And you can also determine if a molecule is polar by evaluating the molecular geometry and the differences in electronegativity. So hopefully you're seeing how all of these concepts are tying together. In the next chapter, we're going to build on this and look at more organic molecules, and then we're going to get into what are called intermolecular forces. And that's where we truly begin to understand how molecules react and why they behave the way that they do. Thanks for watching. If you have any questions, ask on Piazza, in office hours, or recitation. Have a good day.